Section 8.3, to write and evaluate logarithmic expressions and to graph logarithmic functions. The logarithm to base b of a positive number y is defined as follows. Y equals b to the x, then log base b of y equals x. We also have a common logarithm, and that logarithm uses a base of 10. We would write that log base 10 of y, but since this is a common log, we can just write that as log y. We already know that that would have a base of 10 when that is left out. Any other base would have to be written in. We're familiar with families of functions. We already looked at that in the previous section with a parent function of an exponential function. Here, we have families of functions of logarithmic functions. We have a parent function of y equals log of base b to the x, where b is greater than 0, but b cannot be equal to 0. And we are familiar with stretch, shrink, and also the reflection. When our a is greater than 1, then it's a stretch. Our shrink is when a is between 0 and 1. That would be the absolute value of both a. And when a is less than 1, then we know that that's going to reflect over the x-axis. We also know when I have h, internally x minus h, then that's going to be a horizontal shift left or right. A minus sign means I'm going to shift my ordered pairs to the right. A positive or plus sign means I'm going to shift to the left. A plus k means I'm going to shift my function up. And a minus k means I'm going to shift my function down. And we also have a combined function, y equals a log base b, x minus h plus k. The logarithmic function is the inverse of an exponential function. We have seen inverses in previous sections, and we know that an inverse is a reflection of the function over what we know as the identity function. And we know the identity function is y equals x. And that identity function is graphed in green. And you can see I have an exponential function, y equals 2 to the x, and we have seen this exponential function before. And the inverse of that function is y equals log to the base of 2 of x. And you can see that the functions are inverses. It's a reflection of the exponential function over the identity function. And I also have the ordered pairs for each functions shown on the screen. And notice the x and the y becomes the y and the x. In other words, the ordered pairs are flipped, which makes the reflection of the exponential function over my identity function. We'll graph exponential functions later on in this video. Let's look at an example first. A small earthquake occurred within a 50-mile radius of Conneaut, Ohio on September 25, 1998. The magnitude of the earthquake was 4.5. Compare the amount of energy released by that earthquake to the amount of energy released by each earthquake stated below. Here we have an earthquake with a magnitude of 3.6 in Niland, California on 10/14/2013. From the chart on page 446, we can see energy released, which is E, is equal to 30 to an exponent, and that exponent is the magnitude. So what we can do is compare the ratio of these two earthquakes. We put the larger ratio on top, and we have the energy released of the Conneaut, Ohio earthquake is 30 to the 4.5 over the energy released of the California earthquake, which is 32 to 3.6. I have common bases, so I can simplify this ratio to be 30, and we just subtract the exponents. 4.5 minus 3.6 gives me 30 to the 0.9 power, which is approximately 21.4. Therefore, the earthquake in Conneaut, Ohio released about 21.4 times as much energy as the earthquake in Niland, California. Let's look at another one of those examples. Again, I'm going to use the earthquake with magnitude of 4.5 in Conneaut, Ohio, and I want to compare that to an earthquake with magnitude 5.8 in California of 2010. I'm going to put the largest magnitude on top compared to the smaller magnitude on the bottom in a ratio. I have a common base, which is 30, and when I'm dividing, I know I subtract exponents. So that's 30 to the 5.8 minus 4.5. 5. Then what I'm going to do is simplify to be 30, and 5.8 minus 4.5 is 1.3. So I have a 30 to 1.3 power, and when I plug that into a calculator, I approximately get 83.23. Therefore, the earthquake in California released about 83.23 times as much energy as the earthquake in Ohio. In this example, I want to write each equation in logarithmic form. Remember, I have y equal b to the x. In this situation, 144 equals 12 to the second power. 144 is y, 12 is b, and 2 is x. And I want to write it in the form of log of base b of y equals x. So I have log of base 12 y of y, which is 144, equals x, which is 2. Here I'm going to identify my y is 4/9, my b is 2/3, and my x is 2. Again, I'm going to write this as log of base b. So log of base b, which is 2/3, of y, which is 4/9, of x, which is 2. Again, we identify 0.01 is my y, 1/10 is my base, 2 is my x, log of base b is 1/10, y is 0.01 equals x, which is 2. I have log base b of y equals x, which is 3. On this example, I want to evaluate each logarithm. Here I have our general forms of log b y equals x and the exponential form y equals b to the x. And we also have the procedure to perform this operation. The first thing we want to do is write each equation in logarithmic form. To do that, that's going to give me log base 3 of 81 equals x. And that's from the general form. Now I want to convert that to exponential form. That's going to give me 81 equals 3 to the x. Now I want to write each side in the same base. My base is 3, and the exponent is x. So I want to write 81 with a base of 3. So 3 to what power gives us 81? That would be 3 to the 4th. Set the exponents equal to each other. Since the bases are equal, the exponents must be equal. Therefore, x is equal to 4. And then we would solve, but this is already solved for. The next one, log base 16 of 64. We want to write that in logarithmic form. So that's going to give me log base 16 of 64 equals x. Write that in exponential form. Gives me 64 equals 16 to the x. Now I want to write each side in the same base. Let's convert 16 to a base of 4. 4 squared is going to give me 16. But remember, I'm going to drop that x down, but 4 squared is 16 to the x. Now, I think that's correct. I'm going to see if I can get 64 to a base of 4. And that would be 4 cubed. 4 times 4 is 16, times 4 is 64. Now what I do is I set exponents equal to each other. 4 cubed must equal 4 to the 2x. Therefore, I have 3 equals 2 to the x. Now I want to solve. X equals 2/3. We can verify that by substituting x into my problem. That would give me 16 to the 2/3, which we know can be the square root of 16, and then that solution would be cubed. The square root of 16 is 4. 4 cubed, we know, is 64. Again, I want to evaluate each logarithm. Here I want to write each equation in logarithmic form. So I have log. We know this is a common log because there's not a base written, so this is log base 10 of 10 equals x. Since this is a common log, again, the base is 10. Therefore, that's 10 to the x equals 10. I want to write each with the same base. They are in the same base, but recall this is 10 to the x, and this, since there isn't a exponent displayed, we know that it is a 1. Now I just set the exponents equal, x equals 1, and solve, but it's already solved. My next example, log base of 1/4 equals 1. Write that in logarithmic form. That's going to give me log to the 1/4, base of 1/4 of 1 equals x. That gives me 1/4 to the x equals 1. Now what we want to do is get common bases, but we have to realize that anything to the 0 power is 1. Therefore, I can just write x equals 0. 1/4 to the 0 power is 1. Again, I want to write each equation in logarithmic form. That's going to give me log base 5 of 125 equals x. 5 to the x power equals 125. Now I want to get common bases. I'm going to try to get 1 over 125 to have a common base of 5. So I'm going to have 5 to the x equals, I can bring 125 up. And that would be to the -1 power. Then I could get a common base of 5 with 5 to the x equals 5, and 5 cubed is 125, but that would be a -3. Now, since I have common bases, I just set their exponents equal. X equals a -3. I'm going to have log base 2, the 4th root of 8 equals x. Write that in exponential form, which is 2 to the x equals, and then I can convert this to 8 to the 1/4 power. Now let's get a common base. Our base will be 2 to the x equals 2, and 2 to what power gives me 8? That would be cubed. But since I already have 1/4 there, by properties exponents, I know that that's going to be 3 times a 4th, or 3/4. My bases are equal, so then I can set my exponents equal. In this example, we're given the pH of each food, and we want to find the concentration of hydrogen ions, H+. This is given in a chart in our book. And the process to do that, we were given the pH of bananas is 6.1, so we just substitute in 6.1 equals a negative log H+. And we know this is a common log because there's no base given, so we know that's 10. So the first thing I want to do is solve for log H+. To do that, I'm going to divide by -1 on both sides, which gives me log H+ equals a -6.1. Now write that as an exponential form, gives me H+ equal to 10 to the -6.1. Now we're going to plug this into a calculator, and I'm going to get H+ is equal to 7.9 times 10 to the -7. Here I want to determine how many hydrogen ions are in coffee with a pH of 4.3. Again, I want to substitute our pH in, so I'm going to get 4.3 equals a negative log H+. Solve by dividing by a -1. That gives me log H plus equals a negative 4.3. Write in exponential form. This is a common log, so I know the base is 10, so H plus equals 10 to the negative 4.3. Plug that into a calculator, and I get the concentration of hydrogen ions to be 5.0 times 10 to the negative 5.